Very great topic.
Yeah, thanks for having me. Can you see the slides okay?
Yes.
Okay, great. Yeah, so thanks for the introduction. So as Adam said, today I'm presenting some work I did recently with my advisors, Hamid Hassani and George Pappas at Penn, that we're calling model-based robust deep learning. And the theme of this talk is going to be training deep neural networks to generalize to natural out-of-distribution data. And so with that, I'm actually going to start by giving just a taste of the kind of results that we're interested in getting in this paper. So we're going to start by training a state-of-the-art network, something like a ResNet-50, on a data set like ImageNet. So kind of a very standard task. And instead of testing this classifier that's trained on ImageNet on the corresponding ImageNet test set, we're actually going to test it on the newly curated ImageNet-c dataset, which, if you're not familiar with it, is a data set that is very similar to the ImageNet test set, except for it has different kinds of corruptions that commonly occur in natural environments, such as snow or contrast or brightness. So effectively, the idea here is we're going to train this network on ImageNet, and then we're going to test it on this, this test set that has these kind of common corruptions. And we're going to see what happens. And so what we found is when we do this kind of simple experiment on 50 classes of ImageNet, the top one accuracy that you get when testing on this more challenging test set is quite low. So for this challenge on only 50 classes, you would expect the top one accuracy to be much higher than 20% for snow or 40% for contrast. And so what I'm going to talk about today is how to obtain results that kind of reclaim some of the accuracy that's lost when we test on this new test set. So in particular, here's one of the methods that we're going to talk about today. And as you can see in this orange curve, we're able to get back between 15 to 20% of the accuracy that's lost by training on the exact same data. So effectively, what I'm going to try and do today is share our results that allow you to train deep neural networks that are robust against more natural out-of-distribution shifts from the training to the test set. And so with that, let me start off this talk with a few words about safety critical applications. And so by safety critical, I mean any application where the decisions or recommendations of a deep learning system might impact the well-being of humans. And so the canonical example here is, of course, something like self-driving cars, where the detections made by a self-driving car, say of pedestrians in the crosswalk, might dramatically impact kind of the safety of those pedestrians. So this, again, is kind of the canonical example that I often think about when I'm thinking about safety critical applications. But of course, there are others like robotics, whenever you have robotics interacting with humans, or medical imaging, such as when you have a medical detection system that might recommend some treatment downstream for the patient. So the message here with these safety critical applications is that deep learning, when deployed in these applications, has to be robust and trustworthy, since it's going to be interacting directly with humans. And so this is kind of the starting point, these safety critical applications, for what I'm going to talk about today. And the first thing that I want to do is focus on this word robust. So what does robust really mean in the applications, the safety critical applications that we care about? So when we're talking about robustness, the natural place to start, and something that I'm sure many of you are familiar with, are adversarial examples. And I'm talking about adversarial examples here just to kind of motivate where I'm going. And you'll kind of see down the line where I'm leading with this. But I'm going to give a one-slide introduction to what the adversarial example is. So when I think about adversarial examples, I think about data points such as this image living in some Euclidean space, say RD. So this image is just represented by this data point. And around each data point, I'm going to draw some epsilon ball, where epsilon is some small number. And to create an adversarial example, I'm going to do the following. So I'm going to take this original image. I'm going to add some perturbation delta, where delta is just some number that's less than epsilon. And I'm going to create a new image by perturbing my original image x to x plus delta. And I'm going to call this new image X prime an adversarial example if my original image is classified correctly by my deep neural network, so say as a panda, and this perturbed copy is classified as anything else, so in this case, a given. So essentially the message with adversarial examples is adding small amounts of noise to my data can cause misclassification. And this has been kind of well documented in many, many papers. And in particular, this whole community of adversarial robustness has kind of arisen around this idea that adversarial examples are a big source of fragility in deep learning. And what we've seen over the past 5 or 6 years are several thousand papers written on this topic of how to avoid the fragility to adversarial examples. So it's become, in some sense, one of the most important problems that people want to solve in deep learning. But when we kind of consider that this problem of norm-bounded perturbations has been the focus of the robustness community recently, a question might come to your mind, something like, well, if this kind of transformation can cause significant misclassifications, then are there any other kinds of transformations other than these norm-bounded perturbations that also cause kind of poor performance in deep learning? And it turns out that there are quite a few.
Alex,
so yes.
Sorry, there might be an issue with your talk. So is there, I got now already 2. So there are 2, 3 people who say they cannot see your slides. Other people can see your slides.
Okay.
So I can see it on my computer. Is anybody here in the audience that, cannot see his screen right now? Apart from Michael and Yingwei? Okay. I think that might be an issue. Okay. Yeah. So, okay. Sorry, Alex, for the interruption. I think you can just go on.
It's okay?
Yes, it's okay. Thank you.
Okay. Okay, yeah, sure, no problem. Let me know if others can't see the screen and we can figure something out. Okay. So as I was saying, the natural question that you might ask is, well, what other kinds of transformations can cause misclassification? So in addition to these norm-bounded perturbations that we've been looking at, there's also spatial transformations, such as rotating or scaling an image. This has also been shown to cause misclassification. There are out-of-distribution data, where you might have data in one domain and you want to classify well in another domain. There's adversarial patches, where we add some graffiti or patches to the data that you're testing on, or the target domain. There's the sensing mechanism. So this paper from 2016 kind of looked at the problem of does the kind of camera that I'm using impact the performance of my trained classifier? And they found that it did significantly impact it. And finally, there's something that I'm calling natural variation, which is an intentionally broad term that I'm using to encapsulate kind of any kinds of changes that arise in your data due to natural or dynamic environments. And it's actually this natural variation that I'm going to focus on. And I'm going to try and motivate how it differs fairly significantly from the norm-bounded perturbations that we looked at previously. So again, the central question here is, how does data vary in natural environments? So to illustrate this, let's consider the following simple experiment. So say I have a data set of street signs in plain sunny weather, like you can see this image here, and my goal is to classify the street sign in the image. So this is a fairly straightforward task on the face of it. We can train a neural network to classify the street signs in this data set of sunny images, and it would be fairly straightforward. But of course, when we're interacting in a kind of natural or dynamic environment, nature is going to change how these images look. So in particular, when we're deploying our neural network, nature might not show us the sunny image, it might show us an image with snow in it. So as you can see, these two images kind of correspond to each other. They have kind of the same street sign and they have the same kind of roadway, but they differ in the kind of natural variation of the image. So the one on the left is kind of sunlight and the one on the right kind of has snowy conditions. But of course, this isn't the only way that data can vary in these natural environments. So data could also vary according to the amount of rain in the image, or it could have a dirty camera lens, or there could be darkness or fog or blurriness or grayscale or exposure. So this is all to say that when we're dealing with a natural environment, data can vary along many different axes. Whereas kind of in the previous case, when we looked at adversarial examples, data is varying according to the same kind of transformation. So it's always a norm-bounded perturbation. And so given that these kinds of challenges, this adversarial example and this natural variation challenge, seem to be quite different, the next natural question is, well, given that adversarial examples have been shown to cause misclassification so frequently in deep learning, is this also the case with natural variation? And what I'm going to do on this slide is try and motivate to you that, in fact, natural variation can also cause significant misclassification. So again, let's consider a simple experiment. Say I take that data set from the previous slide of images in plain sunlight, and I train a classifier on that data. And then I test on the corresponding test set of sunny images. So if I did this experiment, I would get something like this orange curve at the top, where I'm getting close to 90% performance, which is a fairly good result. And now what I'm going to do is, instead of testing on the original test set, I'm going to test on new test sets with increasingly more amounts of natural variation. So I'm going to start by testing on a test set that has images with slightly more snow. And then I get this red curve. You see the performance has dropped a little bit. I could test on images with a little bit more snow. So this is this kind of magenta curve here. And then finally, I'm going to test on this, this data set of images at the bottom where it's kind of an all-out snowstorm. And as you can see, as I progressively test on harder amounts or more amounts of natural variation, the performance of my classifier goes down fairly significantly. So the answer to this question of does natural variation cause misclassification, at least in this case, is yes. And throughout this talk, I'm going to motivate even more that whereas most of the focus has been placed on adversarial examples from the robustness community, we also need to start thinking about these kinds of natural variation too. So given that this is a problem for machine learning, this natural variation, what are the challenges to designing algorithms that are capable of providing robustness here? I'm going to identify two distinct challenges. So the first is one of modeling. So how do I model the shift, say, from sunny images to snowy images? In the adversarial example case, it's very clear all perturbations are generated in the same way by just adding some noise vector to your data. But here it's quite difficult to analytically write down a function that will map here x in sunny weather to x prime in snowy weather. Now, if we were able to solve the modeling challenge, we would be able to do a bunch of experiments like I had on the previous slide, where we can benchmark the robustness of deep learning to different kinds of transformations. But the model is essential to doing these kinds of experiments. And the next challenge that I'll identify is once we actually solve this modeling challenge, there's the kind of coupled challenge of, well, given a model, how do I design algorithms that can be used to provide robustness? So throughout the rest of this talk, I'm going to talk about these two challenges and how we solve them in this paper. So again, the first challenge that I want to talk about is the modeling challenge. So how can we model the impact of natural variation? To do so, I'm going to introduce what I'm going to call very simply a model of natural variation. And all a model of natural variation is a function g that takes two arguments, x and delta. So x is something like an image, and delta is something like a nuisance parameter, or what we're calling a nuisance parameter. It's something like a vector in R2 or R3. And the idea here is we're going to give this function these two inputs, and it's going to output a corresponding image that has an image that looks semantically similar to the original image, so it's the same street sign, but it has a different level of natural variation. So you can see there's snow in this image. And the idea is if we change this vector delta to something like delta prime, then at the output we'll get another image that has kind of a different level of natural variation. And if we repeat this again, we'll get yet another image that has a different level of natural variation. So the idea at a high level is by varying this nuisance parameter delta, we can produce images with different levels of natural variation. Now keep in mind that I haven't said anything about how we're actually going to obtain this G. I just want to give you some intuition of what the ideal situation here is with these models of natural variation. And later on, I'll talk about how you actually go about learning them. So let's take a closer look at this. again, we have this input image X. Assume we have this ideal model of natural variation from the previous slide. I'm going to consider a set that I'm going to call the learned image manifold. And in a word, this set just contains all the images that can be obtained by passing X and some vector delta through this model of natural variation. And this set is going to look something like a manifold in RD. So RD is the data space. And each point on this manifold is going to correspond to an image that has a different, so you can see that as we go from delta to delta 1 to delta 2 to delta 3, we're kind of varying the amount of natural variation in the images. And this kind of geometric picture should stand in contrast to the epsilon ball formula or geometric perspective that we had when we were thinking about adversarial examples. And this intuition of the geometry will become useful very shortly here. So given this kind of idea that we have this node or this model of natural variation G, I'm now going to try and formulate an optimization problem that can exploit G to provide robustness in deep learning. And so here's the problem that I'm going to think about. And I'm going to move it to the top here. So as you can see, this is a min-max problem where we're trying to learn a weight W of a neural network such that this optimal weight W star is robust against natural variation. And to kind of explain what's going on in this problem, I'm going to break it apart into two parts. So the first part is this inner maximization problem, and I'm going to start by focusing on that. So I'm going to rewrite it like this. And as you can see, this is an optimization problem over this loss functional L, where L is a function that takes three arguments: an image, a label, and the current weight of the neural network that I'm trying to train. And the idea here is I'm going to fix an image label pair, x, y. I'm going to search over the space of deltas and create new images by passing these deltas through the model of natural variation. And I'm going to find the loss maximizing delta star. So in other words, the vector delta that causes my model to get high loss. And what this corresponds to geometrically is I have my learned image manifold from the previous slide. And I'm just going to look at delta 1, and then delta 2, and then delta 3. And then I'm going to find the corresponding image that gives high loss when I push it through my model. So that's the idea with the inner problem. The next step is to look at the outer problem. So I'm going to rewrite it like this. So I'm going to replace this inner problem with this delta star that we had in the inner maximization problem. And by replacing the inner max problem with this delta star that we get, the outer problem looks something like this. So it's just a minimization problem over the empirical risk over our data set. And so given this delta star, we can solve this problem using a first order technique. And the result is a weight W star that's robust against natural variation. So at a high level, this optimization problem is kind of the central object that we're going to be studying toward providing or toward training neural networks to be robust against natural variation. So let's take a step back. I just showed this optimization problem on the previous slide. And what I haven't told you about yet is, well, how do I actually get at this model G? So we talked about G before, but I haven't said anything yet about how you actually go about learning it. And to try and show you what we did in this paper, I'm going to break apart the kinds of Gs that we can learn into two different classes. So the first are known models, and the second class are learned models. So let's start with known models. When I say known model, I just mean any function that's a priori known that we want to provide robustness to. So for example, you'll notice that if we replace g of x comma delta with x plus delta, then we recover the formulation of something like PGD. So this would be useful for providing robustness to adversarial examples. On the other hand, if I replace g of x comma delta with something like r of delta times x, where r of delta is a rotation matrix, I could use this formulation to provide robustness against rotation. But the more interesting case is, well, what if I have something like weather or lighting or contrast? How do I learn a G that models, like, say, the shift from sunny weather to snowy weather? And the answer that we came up with in this paper was, well, let's try and learn it from data. And so in the next slide, I'm just going to show you kind of a brief teaser of what we did to learn these models of natural variation from data in the cases where we're dealing with true natural variation, like weather or lighting. So the idea here to learn these models of natural variation was to use image-to-image translation networks. And I'm not going to go into a lot of detail here, but I'd be happy to talk offline more about the exact details of what we did. So at a high level, the idea was we'll take an image X, we'll encode it into two parts. The first part is a semantic component. So this captures things like the label and what the overall scene looks like. And the nuisance component, which is going to capture things like the weather or any other nuisance in the data. And then we're going to replace this encoded nuisance vector with a new vector that's chosen in a particular way. And then the last step is to decode the original semantic component with this new nuisance parameter delta that I've input into the model. And so this encoder-decoder structure is what we're using here as a model of natural variation. So at a high level, all of the models that we learn in this paper all have this kind of encoding, decoding structure. You can think about it like an autoencoder. Of course, there's kind of more going on under the hood with a couple of GANs that are being learned to facilitate this image-to-image translation, but this is kind of the essential point here. And so then the last piece of this is, well, okay, so I know how to learn models and I've seen this optimization problem. But how do I go about actually solving it? Because even if you give me a known or a learned model, it's still kind of unclear how this optimization problem should be solved. I mean, if W is the weight of a neural network, then the inner max problem is inherently non-concave, and the outer minimization problem is inherently non-convex. So what we're going to do, of course, is resort to some approximation methods to approximately solve this optimization problem. And in particular, the approach that we're going to take is we're going to use alternate steps of solving the minimization problem and solving the maximization problem. And in particular, when we solve the outer problem, we're just going to use plain ADAM or SGD. And so our algorithms are all going to differ in how we solve this inner max problem. And in particular, we're going to propose three algorithmic variants. The first is what we're calling model-based robust training. And what we're going to do in this algorithm is we're going to sample k different delta vectors, and we're going to choose the delta vector that gives the highest loss under our current model. So this is just a 0th order sampling-based technique that can be used to approximately solve this inner maximization problem. The next algorithm is what we're calling model-based adversarial training. And this algorithm is more in line with the adversarial training regimes that you might see in something like PGD or an adversarial training regime for adversarial examples. And so here we're just going to perform k steps of gradient descent on the inner objective in the nuisance space delta. And finally, the last variant that we'll propose is simply called model-based data augmentation. And here we're just going to pick k random vectors delta in the nuisance space. And we're going to create k new images with these different delta vectors by passing them through our model of natural variation. And we're going to add all of these generated images to our data set. So this is truly just a data augmentation technique. And so at a high level, these are the three algorithms that we're going to be focusing on in the experiments. Now, before I move on to the experiments, I want to address one point, which is that it's a natural question you might have is, this seems a lot like data or domain adaptation. Are you just reinventing the wheel, you might ask? And what I want to motivate is that this is a fundamentally different approach to domain adaptation. And here's why. So the first similarity that you might see between these two is, well, you're addressing a very similar problem. So you're addressing robustness to distributional shifts in your data. And while this is quite true, there are some differences. So for example, in domain adaptation, it's very common to train your map between domains or your model and your classifier at the same time with a coupled optimization problem. Whereas in our formulation, we're actually learning models offline, and then we're learning the classifier after we learn the model. So the optimization is not coupled in that way. And to go along with this, the models that you often see in domain adaptation, such as something like a cycle GAN, which has been used quite a lot, is deterministic or unimodal. So it just maps one image from the input to one image on the output. Whereas in our work, we're trying to learn these models that are multimodal. So one image in the input space corresponds to many images in the output space. The next similarity you might see is, well, data is being chunked in the same way here. So you're thinking about data in terms of living in different domains. And this is also quite true, but the main difference here is that in domain adaptation, you think about fixed target and source domains. So you design the problem specifically for two domains. Whereas in our work, the idea has been to, since you're learning this model offline, it can be reused and composed with other models on domains that are entirely unseen during training to provide robustness on not just the data set for which the model was intended, but for many new and other data sets. And finally, there's this word adversarial that seems to be common between these two approaches. So in domain adaptation, this often refers to how you train the map between domains. So you often train some sort of GAN, which is adversarial in nature. Whereas in this approach, we're actually taking an adversarial approach to training the classifier, because we're using this min-max formulation to find the worst case delta. So again, these are just some ways that these two methods differ. And with that, I'm just going to run through a couple experiments and then conclude my talk. So in these experiments, we're going to compare all of the methods that I had on the previous slide to two baseline approaches. The first is just standard empirical risk minimization with something like SGD. And the second is the PGD algorithm, which is designed to provide robustness against adversarial examples. And we're going to compare those again to our algorithms. And we're going to do this over kind of a range of different data sets, as you'll see. So here's the first experiment, and it's quite simple. So the first step is I'm going to train a model of natural variation to map from MNIST with dark backgrounds to MNIST with multicolored backgrounds. And then I'm going to train classifiers using the algorithms on the previous slide with just this data from plain dark background MNIST. And I'm going to test on the test set of these images with multicolored backgrounds. And so what you can see is, well, the model-based methods significantly outperform the PGD and vanilla baselines. But what you might say is, well, this is something that domain adaptation can already handle. And that's quite true. So this is a kind of a very typical domain adaptation problem. And so on the next slide, I'm going to show you something that domain adaptation would perhaps have a harder time with. So let's consider a scenario where you actually have two shifts in the distribution from your training set to your testing set. So say I have a shift in contrast and I have a shift in brightness. But what makes this challenging is I might not have data in my target domain that has both kind of say high brightness and high contrast. I might only have access to data that has either one or the other of those two. So we don't actually have, if our goal is to test our classifier on data with these two different kinds of natural variation, and we don't actually have data for both of these together, what we can do in the model-based case is we can actually learn two models. So one going from low contrast to high contrast, and one going from low brightness to high brightness. And then we can compose these two models together to provide robustness on the composition of these two sources of natural variation. And so what we find is when we do this composition, we can improve by close to 30 percentage points over the baselines. So again, we're providing robustness against several sources of natural variation at once here. The next experiment, which is also something that domain adaptation might struggle with, is we're going to learn a model on one data set D. And then, so we might go from something like MNIST with blue backgrounds to MNIST with red backgrounds. And then we're going to apply this model on a completely new data set. So in particular, we're going to train a model on something like fashion, or we're going to train a classifier on something like fashion MNIST with blue backgrounds. And then we're going to test it on fashion MNIST with red backgrounds. And so again, here's this model that we have. And here's the result of applying this model to 5 kind of similar data sets. And as you can see, despite the fact that this model has been trained only on MNIST, it does a very faithful job of changing the background colors of these other data sets, despite the fact that it's never seen these objects before when it's being trained. And this feature of these models of natural variation that we learned allows us to provide robustness on these new data sets, despite the fact that it hasn't had access to any unlabeled data from the target domain. So I'm going to skip through this guy here. It's a very similar experiment to get to the last experiment. So in this final experiment, we're going to take the QRTSR dataset, which is really nice because it has labels for the amount of natural variation in the image. So you can see the labels are going from 0, where there's no natural variation, to 5, where there's a lot of natural variation. And the first step is we're going to train a model on to map from challenge level 0 to challenge level 1. And so the idea here is we're just going to capture the natural variation shift from challenge level 0 to challenge level 1. And as you can see, this is a very small shift. And we're also going to use this challenge level 0 and challenge level 1 data to train classifiers. So the classifiers and models that we're training for this experiment all have access to the exact same data. So after training these classifiers, we're going to test the classifiers on progressively harder subsets. So we're going to test on challenge level 2, 3, 4, and then 5, and see what happens. What we found was when we test on challenge level 2, all the algorithms, the baselines and the model-based algorithms, perform about the same. But as we increase the challenge level to 3, 4, then 5, we see that the model-based algorithms here are actually significantly outperforming the baselines, which show that despite the fact that we've only used the same data for all of our classifiers, and despite the fact that we've used no unlabeled test data from these more challenging domains, we've been able to provide robustness against this shift from sunny weather to snowy weather. And so with that, I'll just end with a couple of future directions. So there are a lot of ways forward here that I'm excited about. The first is just having to do with the release of the code and releasing a library of models of natural variation to the community so that they can be used in other people's experiments to provide robustness. Because once a model is learned, it only needs to be learned once. And another of these interesting applications is there are many other tasks other than image recognition that are important in the safety critical applications that I talked about earlier. So something like robotics or medical imaging is going to provide really interesting applications for this moving forward. And so thanks.